The next section is on relative topology. Let's see how it starts. Openness and closedness of a subset in a metric space depend on the metric. We have already seen this fact. For example, if you consider this singleton set consisting of the real number 1 as a subset of the set of real numbers, of course, but you consider the usual metric D on the set of real numbers, then in this metric space this is not open. But instead, if you consider the discrete metric on R and get this discrete space, in this space that same subset is open. So things depend on the metric, but actually not just that. Yes, of course, openness and closedness depend on the metric, but they also depend on the ambient space, the underlying space. To illustrate and to make this point more clear, we are now going to consider two examples. Example 12.3.1. Consider this space. You have already seen this before. This is the two-dimensional plane consisting of all ordered pairs of real numbers, and the metric is the usual metric or the Euclidean metric, that square root thing, that thing. And then you consider in this space the subset X consisting of all ordered pairs having their second coordinates 0. Geometrically, this is just your usual x-axis, if you think of it that way. Now you can of course restrict this metric to X. What does that mean? Originally the metric DL2 is actually what? It's a function, right? It's a function whose domain is the Cartesian product R2 times R2 and range is R. Because X is a subset of R2, so X times X is a subset of R2 times R2. So that is why we can restrict this function to that and get this restriction. That restriction is itself a metric on X, and that way we get this subspace of the plane. So this is your one-dimensional subspace, which is your x-axis, as a subspace which is sitting inside the two-dimensional plane. And then you consider this subset E of X. What does E have? E has these points where the X part is a real number lying between -1 and 1. Or you can view E slightly differently also. E is itself a Cartesian product, the Cartesian product of the open interval -1, 1 and the singleton set 0. Alright. Now obviously E is a subset of X, and because X is a subset of R2, so E also becomes a subset of R2. In other words, E is now a subset of these two metric spaces simultaneously. Now the question is this: is E open in this and is E open in this? E is not open in R2, DL2. And the reason is that the point 0, 0 which is in E is not an interior point of E. By that result from the previous section where we had many parts, we know that a subset in a metric space E, say, is open if and only if all of its points are interior points. So because we are saying that this is not an interior point, so E is not open in this metric space. Now we have the convenience in this case of actually drawing everything. R2 is our usual two-dimensional plane in which X is this x-axis and E is the line segment whose endpoints are -1 and 1, which themselves are not parts of E. Okay, so it's like a stick without its ends. Now if I say I am declaring that 0, 0 is not an interior point of E, but say I suppose 0, 0 is an interior point of E, what does that mean? it means that then I should be able to find a ball centered at 0, 0, which is entirely contained inside E. But such a ball looks like this. You have obviously, of course, recognized the fact that 0, 0 is the origin. Any ball in this metric space is the interior of some circle, and when we say that it's centered at 0, 0, that is the center. It's just that with some radius. Now you can clearly see that there are many points which are lying inside the circle that are not lying on the x-axis, and those points which are, for example, above this and below this line, they are obviously not inside E, because E itself is entirely contained in this line. And this continues to be the case no matter how small a radius of this ball you choose. No matter how small the radius is, there will always be some points inside the ball which are lying above the x-axis and some which are lying below the x-axis. They will prevent such a ball from being entirely contained in E, and that is why 0, 0 is not an interior point of E, and as a result E is not open in this metric space. But as we will now see, E is open in this metric space. But E is open in this metric space, that is our x-axis, and this is because of this fact that the ball centered at 0, 0 having radius 1 in this metric space is E itself. Why? Without going into the actual details, you just see here in this figure itself. So we are thinking of a ball, an open ball, whose center is 0, 0, okay, and the radius is 1. That means it consists of those points whose distances from 0, 0 are less than 1, and at the same time, and this is important, that is why we have this cumbersome looking notation below this ball B, that in this metric space, those points have to lie in X, about which we are talking that they are having distances from 0, 0 which are all less than 1. So those points will be these points and these points, but together they just give us E. So E itself is a ball in this metric space X, and by that result, I think part C, I don't remember exactly, in part C of that big result in the previous section, every ball is itself an open set. So that's how E, in spite of not being open in the larger space, is open in this smaller space. Do you see how we no longer have these problematic points which were present in the previous ball in the larger space? In this space, the balls are open intervals. In the larger space, the balls are interiors of circles. So not only the metric but the ambient space also has an effect on which sets will be open and which will not be open. Next we have example 12.3.2. Here we are considering the usual metric space of real numbers, where D is the standard metric, that absolute value metric. And then we consider the subset X, which is this ordinary open interval -1, 1. So just like the previous example, here also if we restrict the metric D to X, then we get this subspace. Alright. And then we consider the subset E, which is this closed open interval 0, 1, subset of X. It's obviously a subset of X, and because X is a subset of R, so this is also a subset of R. So similar questions arise here also. But this time we are not going to talk about openness of E, but rather closedness of E. Is E as a subset of X closed in X? Is E as a subset of R closed in R? And the answers are these. E is not closed in R comma D, which we already know. I mean, this is not a closed set in the usual real line. That is because 1 is a boundary point of E. Why, that I leave to you to verify. Okay, you go back to the definition of boundary points and show that 1 is neither an interior point of E nor an exterior point of E, and that is why it has to be a boundary point of E. But 1 does not belong to E. By the definition of a closed set is a set which contains all of its boundary points. So that is why E as a subset of R comma D or as a subset of R is not closed. But E is closed in this subspace. Let's see also exactly how. The reason for E to be closed in this subspace is this, that the complement of E in X is this open interval -1, 0, which is open in X. And here we are using one of the results. One of the results means one part from that big result having many parts from the previous section. That if the complement of a subset in a metric space is open, then the subset is closed. So these two examples show that we have to really be careful when saying something like a subset is open where, in which metric space. So that is why we need a new terminology. So we have this next definition 12.3.3, relative topology. Say your X comma D is some metric space in which you have a subset Y, and in Y you have a subset E. Okay, so you already understand why we are taking these things. We say that E is open relative to the subset Y if E is open in this subspace. Y as a subset is a subspace of X which has this metric that it has inherited from the metric on X, which is just the restriction of the metric to Y. And there is this, the closed set part also of this definition, which is this. We say that E is closed relative to Y if E is closed in that subspace. Alright, so we have got a term closed relative to, open relative to, two terms. That is fine. But now, is there a way of recognizing, say you are in a situation like this. Now, can you somehow say, without actually going through the trouble of verifying it, that E is open relative to Y? If E satisfies some properties, then can we just simply say, by looking at those properties, that okay, yes, E is open relative to Y, and similarly, is there some criterion that will allow us to say that E is closed relative to Y without actually going through the verification? And yes, of course, we have a result, and that is this proposition 12.3.4. And again, the setup is same. You have a metric space X comma D in which there is a subset Y, and inside Y there is a subset E. So this is the criterion for openness of E in Y. E is open relative to Y if and only if E equals V intersection Y for some subset V of X which is open in X. To put it more simply, E is open relative to Y if and only if E is the intersection of Y and an open subset of X, like V. And the criterion for E to be closed relative to Y is exactly similar. E is closed relative to Y if and only if E equals K intersection Y for some subset K of X which is closed in X. This time, because we are asking if E is closed, so K is closed. Now the proof of part A is available in the text. So I want you to go through the proof. If you don't understand any part, please let me know in the comment section below. And the proof of part B is the only exercise of this section that we will solve in the next video on analysis.